Hey, you guys, let's see what is next. It's time to talk about differentials. So what is this all about? That name kind of sounds similar to differentiable, right? Differentiable means the derivative exists. So obviously there's something similar here. We're talking about derivatives. Okay, not a surprise, I guess. So imagine we have a function that's curving somehow. This drawing right here will give us a good example, f of x. On that function, we've got a point. Let's just call it x comma y. Let's think about the tangent line that passes through our point at xy. Okay. Sure. All right. Sounds good. And then let's draw some lines off of xy like so. So we're going to draw this line coming out horizontally and then going up through the tangent line all the way to the function. Now what we've done, even though we've drawn that vertical piece all the way up to the function, focus on the triangle created by that right angle and that tangent line. We're going to label the horizontal distance of that triangle and the vertical distance of that triangle. Here's what we're going to call them. We're going to call the horizontal distance dx. We're going to call the vertical distance up to the tangent line dy. It turns out the dx and the dy are the differentials. They're the lengths of the two legs of our triangle. Now, if you look carefully, notice that the dx, right, is like a run, and the dy is like a rise. The rise over the run. Check this out. We take the rise over the run. That would be dy over dx. That's also, right, rise over run would tell us the slope of our tangent line. So this ratio of dy over dx telling us the slope of our tangent line, and of course we refer to the slope of the tangent line as f prime of x. Oh man, that's so cool. All right, so before I told you guys when we introduced Leibniz notation, where we called a derivative dy over dx, so I told you lots of times that that was not a fraction. Turns out it is a fraction. Okay, so I wasn't really lying to you though, because back then we weren't thinking of it as a fraction, and it would not have been helpful for me to say, well, it kind of is a fraction. We'll talk about that later. We just wanted to think of it as the derivative of y with respect to x. But it turns out this notation is really insightful because we can think of numerator and denominator separately if we think of the differentials, the rise over the run. And of course, that's equal to the slope of our tangent line. So we'll say it's equal to f prime of x. Now, if these really are two different values, dy over dx, then we're allowed to multiply the dx to the other side and get this equation. Dy equals f prime of x times dx. And turns out this is going to be really, really useful for us moving ahead. Just to be really clear, what do we mean by the differentials? Okay, so dy is the differential of y, dx is the differential of x. And if we take the ratio, the differential of y divided by the differential of x, then we get the derivative of y with respect to x, dy over dx. But we can separate them. The point here is we can separate them and think about them on different sides of this equation. Okay, they're different values in and of themselves. Let's practice this with a couple of questions. So I'll keep dy equals f prime of x dx on the screen there. Let's try this out. Find the differential dy for each of these functions here. Y equals x to the 2/3. Let's try it for that, something relatively simple. And let's also try it for y equals t plus 1 over 2t minus 1. Okay, gonna switch. Find the differential dy, okay. Part A, y equals x to the 2/3. So here's what we're gonna do. We're going to take the differential of both sides. The differential of y is dy. The differential of this side, we need to take the derivative as normal, 2/3 x to the negative 1/3. But then multiply that by dx, the differential of x. And there you have it. And that's it. We've got the differential dy. dy equals 2/3 x to the negative 1/3 times dx. Notice it's dy times the derivative of our function, then times dx. Let's try out something a little bit harder. Y equals t plus 1 over 2t minus 1. Okay, so what we'll do is say, all right, well, for the left side, the differential is simply dy. For the right side, I need to take the derivative. That's going to require a quotient rule. Low d high minus high d low all over the low squared. And once I've got that derivative, then on the end, I can multiply by the differential of the variable I'm using here. So that's dt. And probably here, I'm going to go ahead and simplify that derivative. Turns out this one simplifies pretty nice. 2t minus 1 minus 2t minus 2. The 2t, subtract 2t, those cancel. Then we've got negative 1 minus 2. We've got negative 3 over 2t minus 1 squared dt. There we have it. Okay. So some good practice on how we work with differentials. Before we get into some more challenging examples, what do we have next? Let's take a look at these. Next example, let's approximate the square root of 4.37, but this time using differentials. Okay, so it turns out we can do all of those approximations with differentials as well as with our linearization. Then I'll come back and we'll get to that last example in a moment. Approximate square root 4.37 using differentials. Okay, here's what we're going to do. When we're using differentials, we're going to say y equals square root of x. Before, when we did the linearization, we thought of it as f of x. With differentials, we want to think of it as y. Okay. Also, check this out. When we find the derivative of both sides, right, this is x to the 1/2. Differential, and then this differential, 1/2 x to the negative half dx. We can rewrite that 1 over 2 square root x dx. Okay. How is this going to be helpful to make this approximation? is what we're going to do. We're going to think of x as equal to an easy value that we can plug in here. So when using differentials, we're going to take x to equal 4. Notice we also have a dx. The dx is the difference between our value of x and the actual value. We're going to take dx to equal 0.37. So again, x is the number that's close to this that we can easily plug into a square root. Dx is the difference between that number and the thing we're trying to approximate. Check out what happens. Plugging those numbers in, 1 over 2 square root of 4 times 0.37. Grab your calculator. What do you get for dy when you plug those in? Right? This is going to end up being 1/4 times 0.37, 0.0925. Does this decimal look familiar compared to the first time we did this? That was the decimal, at least the decimal portion of our final answer. Okay, what is this? This is the change in the y value. In a minute, I'm going to draw you a picture kind of like that differential picture that we did a second ago with the triangle. Explain what this is, why that's the change in y. To get the final answer, what are we going to do? We're going to take this change in y and we're going to add what would have been the original y value. Okay, so if we have y equals square root x and we took x to be 4, add the y value for x equals 4. So for us, that was y equals square root of 4, which was 2. So we're going to take 2 plus 0.0925. That means our final answer, 2.0925. It's the same answer we got before. How did this work? What is happening here? This is crazy and amazing. Okay. A drawing. So square root of x, something like that. Let's say 4 is right here. Okay. There's a tangent line there. Okay. 4.37, let's say that's out here. Think of the triangle, all right? So the triangle is going to come out and line up with the 4.37. Then it's going to go up. There's our little triangle. The triangle goes up to the tangent line. So here the curve actually passes underneath instead of above. But that triangle is on our, up to our tangent line. Right? Remember, we said this was dx. We took dx to be the 0.37. That's the distance between our 2 points. That makes sense. Dx is how far we moved horizontally. This portion is dy, going all the way up to the tangent line. We found that to be 0.0925. Just this little distance. So if we're trying to find the approximation, the point that's on the tangent line itself, well, we need to take that little distance and we need to add, right, the y value of the original point, which was 2. So we started at 2, and then we added on that little bit more, add them up together. There's our approximation, 2.0925. Pretty amazing. Okay. You know what? Let's stop this video here and we'll do the last example next.